Hello, I'm Joaquin van Schoten. Welcome to our course in machine learning. And in this first lecture, we'll talk about a few interesting things to know about machine learning to get everybody on the same page. So first of all, you may wonder, why should I study machine learning? Well, machine learning has been part of many tools we use every day. It will be more useful in the future as will help self-driving cars. And it's a crucial part of basically any science that we do today. First of all, we have many products like search engines. Google learns what you're looking for while you're Googling. So for instance, when I search for machine learning, it will give me different results than when you Google machine learning, basically because it has learned over time what I'm typically looking for. Similarly, Netflix learns what you like and gives you recommendations so you can find interesting movies faster. Google Translate is now pretty capable at translating websites and other documents. Again, using, in this case, deep learning to translate between languages. We also are pretty good at understanding speech. Tools like Siri and Alexa do a reasonable job at understanding what you're saying and then doing the right actions. And very interestingly, they're also good at gameplay. For instance, AlphaGo is a system developed by DeepMind, which beat the best human Go player. And this is interesting because it shows that you can use machine learning to make strategic decisions, which will definitely be useful to make our lives easier. And one of these applications is self-driving cars. Hopefully in the future we won't have to drive our own cars, we will have safe cars that drive themselves. Also, in the doctor's office, whenever you need a drug or a treatment, in the future a doctor will be able to look at your DNA and then prescribe drugs which are specifically designed for your genetic makeup so that you have less side effects and the drugs work better. And basically in any science today, genetics, astronomy, neurology, and so on, it's pretty much based on machine learning all the way because these sciences, they produce so large amounts of data that a human can never really manually look at them. For instance, in astronomy, there's a telescope that scans the entire sky every couple of days, producing petabytes of data. And we need machine learning techniques to basically filter that data and recognize interesting things and then report them to the humans to look at more closely. Now, what is machine learning? Well, compared to what humans do, when we want to learn a new task, like riding a bike, we do it by gathering experience. We try to ride a bike, sometimes we fall down, and that's a learning experience. And over time, we collect more and more data, we collect more and more experience, so we get better and better and better at a task. And when a machine wants to learn to perform a task, it works basically the same way. So we provide experience in the form of examples, typically some data X, and then we want this machine to become better, to minimize some kind of error given this data X. For instance, say you want to build a system that recognizes people in images, then the data X is a large set of images, typically labeled with the name of the person that's in the image. And you want to minimize, for instance, the misclassification error, the amount of errors in recognizing people. Now, typically, not always, but typically, we address this by learning a model or function f. And this function f has to take the inputs x and then produce the outputs y. Now, this function f, we cannot know this function beforehand. So what we can do is to define a general function f, which has a number of model parameters, variables, that we can still change in this function. So these model parameters, theta, we want to learn the optimal set of values for theta that produces the right output y. So mathematically, I do try to minimize the amount of math in the slides, but sometimes it's very useful to explain stuff, and so I will gradually build up and include more math in the slides. So we're having function f, which is given some input data, for instance, images x, has to produce an output y, and this function f has a number of model parameters. It could be 10, it could be a million. And if we find the correct values for these model parameters, then this function f will exactly give us the right output y, hopefully. So the whole exercise is to find an algorithm that can solve this problem. Basically, find the set of model parameters theta which minimizes the error produced by this model. Right? And typically we do this by having a set of training points x and training labels y, for instance, or training outputs. And then we kind of use some kind of optimization technique to find the optimal values for these parameters theta. Okay, now two things here. First of all, this data x doesn't appear magically, right? Typically, a machine learning model is part of a much, much larger system which has to provide the right data x to the model. The system needs to collect the data from somewhere, the sensors involved, and so on. The data needs to be cleaned, it needs to be normalized or otherwise preprocessed so it's in a nice shape that the model can work with. And very importantly, you also need to check the data for biases. A very famous example, for instance, is in image recognition, in which an American company built a very good visual recognition system, but it worked very well on white people, but less well on black people. And the reason for that is that the data it collected, the images X, were collected in the United States and were mostly about white people. So that's dangerous, of course, right? Because then your model is not actually learning the task correctly. It's biased by the data. And if your data is biased, then this function you learn will be biased. So your model is biased. Right? So that's definitely something you need to keep an eye on whenever you build a machine learning system. The second thing is that we don't actually know the best shape for this function f. And there's actually a theory that says that there is no perfect shape for the model f. It always depends on the task. And so we have to make some assumptions about what function f, what shape of function is good for solving this task. And so all these assumptions we call an inductive bias. These are all the assumptions that we, the designer of the system, make about what this function f should look like. Everything except the input data x. Right. So one obvious thing you can do is say, well, if this function f is supposed to recognize people in an image, we have a thing called the human brain that already does this, right? So we can try to model the human brain inside of function f. And that's, of course, called a neural network. So this typically consists of a number of input nodes where the image goes in, and then typically you have many layers, and these are all connected, and then this is an output, y, and then basically all these connections, these netted connections, they have a weight, theta. This is our theta y, and so we have a lot, sometimes millions of these weights that we have to learn. And if we can learn these weights correctly, then this function f, basically, given the data x and our learned model parameters theta, will give us the right output y. This is one example. Another thing you can do is say, well, the output y is probably some kind of logical combination of inputs, right? So if our input x is a table with a lot of columns, and say these columns we call x0, x1, x2, and so on, then we can say, well, our model could be represented as a tree, and which we have logical tests. For instance, say that x1 is larger than 5, then we go on the left, otherwise we go on the right, and say that x2 is more than 3, then we go yes, and we say no, and this is for instance yes again. Right? So in this case, our model is represented as a tree. And our parameters in this case are the tests we do in the structure of this model. Another thing we can do is not actually having a mathematical model, but rather a function that returns to us a target based on similarity. And this was done in nearest neighbors. So say we have the feature x1 and the feature x2, and we have some positive points. These are all positive. There's some negative points, and then we have a new point that we want to classify. What we can do is basically look at which points are nearby, and then make a decision based on that. Okay. This is what nearest neighbor does. SVM does this also in a bit more intelligent way, which we'll cover later. And finally, another thing you can do are Bayesian models, in which case our function f is a probability function. Right? So say we have, I'll try to draw in 3D here. So we have function x1, x2, and this is basically some kind of, this is like, hopefully you can see this. So it's basically like the 2D distribution, right? This is the projection of this, right? And basically, we want to learn this probability distribution f in this case, which then gives us probability. This is a probability p, right? So that, for instance, say that these inputs x1, x2 are pixel values, then we say, okay, if the pixel values are like this, x1 has value this, x2 has value this, then this is very likely to be a person that you want to recognize. Or if it's somewhere here, it's much less likely to be the person. Right? So we learn these distributions f like that. This is called Bayesian modeling, and we'll talk about that later. All right? So different ways to build this function f. Now, on top of that, this function f can have some what we call hyperparameters. So these are all user-defined settings. For instance, if you build a tree, it can be how deep this tree should get. We can constrain that manually. If you want a neural network, we have to make decisions such as how many layers are there in the network, how many neurons are there in each layer, what type of neurons are they? Are they like normal? This could be like ReLU-based. We'll talk about it later, what that all means. Based neurons, or it could be like evolutional neural net and so on. So all these decisions we have to make, and all these decisions we call hyperparameters. Yeah. And then there are assumptions about the data distribution. So many models actually make this implicitly. And one very common one, for instance, is to assume that if we have a variable x, that the values are between 0 and infinity, right? That the values are somehow null distributed, right? So if you would draw a distribution, then it would look like this, right? It's much more likely that the values are somewhere here and not always they are there. So many models make this kind of assumptions, and if the data does not adhere to these assumptions, then the model won't work well, and we may have to pre-process the data before the model can actually learn something well. Okay. So this is all negative bias. Now, of course, as a human, if you do a lot of machine learning over time, you kind of learn which technique to use for which kind of task, or which sub-techniques to use for a certain task. Now, in principle, we can also learn this, right? So if we have seen many tasks and we've trained many models, we can learn across those models to learn how to build a new model later on. This is called learning to learn, or meta-learning. Some examples of this are choosing the right models. We can look at the data and then decide which model to use, deciding which hyperparameters we should use, like for instance the structure of the network. And sometimes we can even reuse previous model parameters. So say we have a neural net that we train on a lot of images, and over time we have learned the optimal set of weights theta. What we can do, so if we have then a new task and new outputs, instead of starting from scratch, we can start from a network that was pre-trained and then maybe add a few layers at the end and maybe freeze those or unfreeze those. Different ways we can do this. We can sometimes, instead of starting from scratch, copy the model parameters that we learned from previous models so we can learn the new task faster with less data. So on a high level, this means that the problem we want to solve is to find the optimal set of theta model parameters, which we learned from data X, and the optimal set of assumptions about the model so that the model we end up with gives us the lowest possible error. Right? Now, this is all high level. Now let's look in a bit more depth at how we do this. The first question I often get asked is, what is basically the difference between machine learning and statistics? And Leo Breiman wrote a brilliant paper about this. It's called Statistical Modeling: The Two Cultures. It's in the reading materials. And basically what it comes down to is that both fields try to make predictions of natural phenomena. So we have an input X, and then there's some natural process that produces an output Y that we want to learn. Now in statistics, we basically want to help humans understand the world. So we kind of make assumptions about what this function, this process looks like, and we model that using understandable models like linear regression, logistic regression, Cox models for health data, for instance. And we then fit these functions to our data, and then afterwards we look at the model parameters. We look at what the tree looks like. We look at what the linear model looks like. And that helps us understand the world. It helps us understand which variables are important, which ones are not, how they interact, and so on. Right? So statistics helps us to understand the world based on data. In machine learning, we kind of assume that we cannot ever learn this function so easily. Right? Say, for instance, that your task is to recognize your mother in an image. It's very hard to imagine a model that we can actually explain. You cannot explain to somebody how you recognize your mother. It's very sub-symbolic. It's very inexpressible. Right? So instead of assuming anything, we kind of assume that this process is unknown, but we can sort of approximate it using things like neural nets. And the goal is then not to understand this model per se, but to automate the task entirely. Like a self-driving car. A self-driving car doesn't explain to you how it drives, but it just does it for you. Right? It just replaces the human task so that the human can spend his time doing more interesting things than driving. Right? So yeah, now typically we can get some understanding of what the neural net is learning. We have some different visualization techniques and so on, in which we can look at the model and see what it has learned and whether it has learned something useful. But the individual weights of the synaptic connections don't have individual meaning themselves. Right? That's the big difference. A criticism, of course, of machine learning, but this is very engineering oriented, right? So any function that fits here well works, right? And there's relatively little mathematical theory about how to build neural nets or to understand whether a neural net is correct or not. There's some, and we're desperately looking for more mathematical theory. But in general, there is no simple way. So we just kind of have this shortcut in which we just try to model the data as well as possible. Okay. Okay, which types of machine learning do we typically deal with? First of all, there's supervised machine learning. So in that case, we want to learn a model F based on label data. So we have some data X, like images, and labels Y. For instance, say we want to build an automatic astronomer. What we do is basically we have some data. So say we have some stars here. And maybe we have some like a galaxy here. So we collect a large data set, and somebody then needs to label all these images, like this is a star and this is a star and so on. And then over time, we learn to recognize stars and galaxies. So if you have a new star, our model can predict whether this thing is a galaxy or a star. This is supervised learning. So somebody provides labels so that the system can learn to recognize things. Now, sometimes we don't have labels. Sometimes we just have dots, some points in the space. Okay. Then we can still do interesting things. We can, for instance, learn whether there's a structure inherent in the data. Right? So if you have, for instance, these dots here, you can say, well, this is a cluster of stars, and this is not a cluster of stars. Or maybe there's something here which looks totally weird, and this is an anomaly. This is an anomaly, right? So things like clustering, anomaly detection, and so on. These are all typically unsupervised because there are no labels. Sometimes we have some labels, but not a lot. So say this is a star, and yeah, so this is a star of cluster 1, and this is a star of cluster 2, and we have a new star here. And you want to know, does this belong to cluster 1 or cluster 2? Now, it's hard to make this decision based on this data alone, but imagine that we have a lot of other points which are not labeled, but we know where they are. So say we have all these points here. Now, we can, even though these points are not labeled, they are useful. They help us understand that maybe this point here belongs to that cluster, so it's more likely that this point will be classified as belonging to cluster 1. That's semi-supervised learning. And then finally, there's reinforcement learning, where you have, so this is most similar to, for instance, learning to ride a bike, right? So you have an agent, like a child, that wants to learn a task, like driving a distance on a bike without falling, and it does this by trying, and then based on these trials, if it does something right, it gets a positive reinforcement. If it does something bad, she falls down, and that's a negative reinforcement. Right? And based on the feedback from the environment, you try to learn a task. So we'll get back to this later on. Now finally, in practice, many real-world systems have a combination of a few or sometimes all of these. Okay. Right, so first, supervised learning. So here we have an algorithm, and we're given data X. We give it labels Y. This is a function F, which has to, this is our model, this is our algorithm, and finally, after we're done, we have learned the optimal model parameters, so you have predictive model. And so now if you have a new input X, we will get a new output Y. Now, if Y is a class, like a star, another star, that's called classification. If Y is a number, like for instance a temperature, then this is called regression. Right? So regression is simply supervised learning where the output is a numeric value. And we'll talk about many supervised algorithms in this course, and typically many of these can do both classification or regression. They can sometimes do one better than the other, but often they can do both. Here's, for instance, classification. So here we have two classes, the green and the blue and the red. For instance, this can be spam emails and non-spam emails. And this feature these features here could, for instance, be the occurrence of words, right? So say that this is a number of times that the word Nigerian prince occurs. This is a number of times that the word machine learning occurs, or the n-gram machine learning occurs. Then this model can learn, okay, if there's a lot of talk about Nigerian princes and not a lot of talk about machine learning, then this is likely a spam email. If there's a lot of talk about machine learning, it's probably not a spam email, hopefully. And then we can try to learn a function that then separates that, right? So in this case, we have a linear model, logistic regression, that draws the boundary here. This we call decision boundary. We typically cannot see this boundary. Sometimes we have, like in this case, we can plot it analytically, but often we don't. It's a boundary where you shift between the predictions. And in this case, we just draw it by just predicting every possible point in the space. Okay, so this simple linear model produces this output. This is our model that we've learned. We learned the parameters which define this linear line here. And then we can make predictions. So in this case, we see that the model makes some mistakes. So these blue points here are misclassified as spam, while they're not spam, while these red points are classified as not spam, while they are actually spam. Now, this is typically what you see in textbooks. In principle, most classifiers can also return to you a probability or a decision function, some kind of number that tells you how certain it is about a prediction. And so we see that actually around this space, it's like here's quite clear it's not spam, here's spam, and here's quite clearly not spam. But in the middle, there's not actually a sharp boundary. Like it's only maybe 40% sure that this is spam, or 60% sure that this is not spam. So, and it's typically useful to look at how sure the model is when you make predictions. Okay. Now, this linear model is only one of possible models. You can also replace this by, for instance, a supervised machine. And you can see the supervised machine can learn much more complex models. Right? The supervised machines are based on similarity. So it will single out some points which are important to remember. These are called support vectors. And when you want to classify a new point, we see how far that point is to the different support vectors that are selected based on this data. And anyway, we get back to that. What we'll see is that this model it can learn very complex shapes. Typically, there are like blobs around these support vectors. And here the same for blue. And we can see that it learns something more complex. You can also see that, like, this linear model here was like super sure that this is not spam, while this SVM is not so sure, right? So it hasn't seen any data in this area, so it's not so sure that this will actually be. It's probably not spam, but it's not entirely sure either. So again, looking at this probability is definitely useful. And then finally, we can also use KNN, k-nearest neighbors, and we see that KNN typically has this kind of very rugged shape. It's a very flexible model, so it kind of bends around points, individual points, and so on. It also has this little like enclave here, so it kind of predicts these points blue because there are these 2 points here, which may be good, but these 2 points may also be just noise. And then this model is what we call overfitting. We'll get back to that. So different classification models learn different types of functions. And we'll have to choose basically which ones are most useful for the task that we want to solve. Okay, so how would you solve a problem like this in practice? So say we have these 3 types of irises: versicolor, setosa, and virginica. Now you're asked to build a machine learning system that recognizes these flowers, and well, there's different ways you can do that. One thing you can do, for instance, is to collect lots of images, right? Lots of images of this kind of flower, lots of images of this kind of flower, and so on. And then you can train a deep learning model that looks at these images and then tries to recommend which flower it is. Now, you can do that. What you can also do is to use domain knowledge. If you know that the size of leaves is an important indicator for recognizing flowers, what you can do is manually measure the size of these leaves. Then we get like the sepal length, that's this, the sepal width, the petal length, and the petal width, so 2 types of leaves. So we end up with 4 numbers for every flower, and then the class. And then these 4 dimensions may be an easier representation of the data. If you plot these in 2 dimensions, we can see that simply the sepal width, sepal length, and petal length together plot the points into blobs which are easy to distinguish. You can easily learn a model that separates the blue points from the other ones, for instance. Okay. So this representation of the same data makes it easier to learn this model. This is one very critical thing about machine learning, is to think about how should we represent the data so that we can do useful things with it. But sometimes we don't need a million parameters to recognize this. Sometimes we have a simpler representation that makes the problem simpler for us. Okay, that's classification. Regression is similar. So again, we have a label. In this case, the label is a number, the target. And we have input x. In this case, this is the input x. We only have one input x, and we have output y. Right? And so we have a function that, this is a function here, f, which predicts y given x. Right? Now, we can see that this linear model here, it does best, but it's basically insensitive to any kind of patterns that are in this data. So it may not be the best model. We can try other models. First of all, we can try Bayesian models. In this case, we don't not only get prediction, but we also get an uncertainty interval. We get it doesn't say its value is 0, it says it's 0 plus or minus 1. So it gives you an uncertainty interval, confidence interval, but it's typically very useful to use. We can also try more complex models like Gaussian processes, which we'll see in a couple of lectures. Not only can this model learn very complex functions, it also gives you very good uncertainty estimates about where it expects there to be. These are all examples of regression models. In unsupervised learning, we don't have labels y, we only have data x. And the typical example here is clustering, and you've probably seen k-means before. We won't talk too much about these. This is just for background. So here we have k-means, which learns to cluster these points into different clusters. Sometimes it does a very good job. Sometimes it's not so good. Like in this case, it kind of, it separates the cluster here. Because you tell it to build 3 clusters, it will build 3 clusters. But sometimes it makes some kind of weird decisions, so we need to kind of be careful when we do this. There are different ways to evaluate a clustering, of course, which will be covered in other courses. This is one thing you can do. Another very interesting thing you can do is if you have a high-dimensional data set, which is difficult to understand, it's possible to learn what we call an embedding. An embedding is basically a new representation of the data, typically in fewer dimensions. Sometimes it's more, that depends on what the application is. But typically it's in fewer dimensions. And so we have this very complex 3D data that we can now express in 2D, hopefully preserving the information that was in the original data. And what most of these methods do, like PCA tries to preserve the variance, and LLE, local embedding, tries to preserve distance between the points. And this gives rise to very different kind of embeddings. It's typically a very useful way to properly process your data before you give it to a machine learning technique. Or sometimes these embeddings are so good that you don't need machine learning. You can just look at the data after a presentation and you're done. And then finally, there's reinforcement learning. So here you have an agent. So say, for instance, you want to develop a system that plays Go, which you can do. So here the environment is kind of some function that evaluates the quality of your board. Your state is a board that you have. And so based on a certain board, your agent has to decide to move upon or to add a stone on your Go board. And after you do the action, you are in a new state, and you also get a reward. So if you do a good action, you get a positive reward. If you do a bad action, you get no reward or a negative reward. Sometimes it's possible that you don't get a reward immediately. Sometimes you have to do many actions. You do this group many, many times, and only after a number of times do you actually get a reward or not. So this agent, what it has to do, it has to learn a policy based on the state. This case, the state is some kind of, the state can be some function x, and there's an action y, and you have to kind of learn a policy f that produces the right y, given the x. Nowadays, this agent is often represented by a policy network. It's kind of a simpler, well, quite simple neural network that has to basically predict the action based on the input x. The critical thing here is that you need a good way to represent your state. Like, you need a good way to represent your Go board or chessboard. And the better this representation is, the better your model will do. Okay, so we've seen different techniques like neural networks and trees, and these seem like all very different techniques, and they are. But they also do share very similar structure. And basically all machine learning algorithms have the same structure, and they always consist of three components. First, there's representation. Right? That's the shape of your model F and your hyperparameters. Right? So your model F must be represented in a formal language that the computer can handle. Like if it's a tree, then we have to say, well, this function F is tree-shaped, and we have to decide which things to test on. Right? So the representation defines the concepts you can learn. Another representation is a neural network. I'll get back to that. Then you need an evaluation function. Right? So say that we have two possible trees. You want to know whether this tree is better than that tree. Okay? And so to know that, you need a loss function. It's some kind of internal function that tells you which of the two hypotheses, which of the two models here is better. So that you can make decisions. So if this one is better than this one, then you throw away this one and you can do this one. Or say that maybe, So if this one is better than this one, then you go here and then you continue growing the tree in this direction. And then separately, you need an optimization technique. That's a method that defines basically how you fine-tune your model. In the case of decision trees, this is an algorithm called Hunt's algorithm. It's kind of a recursive optimization technique, which either like starts from a simple model, like in decision trees, you start from a simple model, like one split, and if this model is not good enough, you refine it or you relax it, right? Until it puts the data. Another thing you can do, typically for neural nets, is you start with an initial set of model parameters, basically all zeros or near zero values, and you gradually update the values of all the synaptic weights until the model fits the data. Okay. So basically any algorithm, any combination of these three things represents a valid machine learning algorithm. If you can represent the data according to some function f and some model parameters theta, you have a way to evaluate which theta is better than another set of thetas, and you have a way to optimize this model parameters theta, then you have a valid machine learning algorithm. And there's lots of imaginable things. The problem is that you want some combination that's powerful and flexible, right? Because not all representations have a good optimization technique. Right? So you need a combination of these three things that works really well. So one example of this are neural nets. So in this case, a representation is a neural network. So first of all, we have to decide how many layers, how many nodes in this layer, and so on. And then every connection here has a weight. So this will be theta 1, theta 2, theta 3, theta 4. And all the inputs will have values. So this will, for instance, get pixel values. So this will be x1, x2, x3, x4. And then what this node does, it will weight the input by this weight theta 1. So what comes out here is basically the sum over my inputs multiplying the weight by x1. Okay. This is what's inputted, and typically these neurons have a certain activation function. Well, it's just not called f, not called g, whatever. Activation function that takes this input, typically also has a bias that kind of defines when to give an output or not. And again, there's different ways you can do this. Sometimes this parameter g can be like a sigmoid function, so it only predicts an output if this sum here is, this can be the bias b here. So if you are if this gets larger than the bias, you get an increasingly positive result. This is called a sigmoid function. You can also do like a ReLU, where its output is always 0 unless the weighted sum of the inputs is higher than some bias b, and then it will produce an output, and so on. Right? So this together is your function f, and finally what comes out is, again, the weighted sum of all these is then the output. So this together is our function f. Okay, so important thing is, well, first of all, we need to set the higher parameters, like the type and the number of neurons. And separately, now we have basically simplified the problem in a way to finding all these values theta. Right? So if we can find these 4 times 20 plus 25, so here we have 25 parameters to learn. When we have learned those 25 values, then we have learned our model. We've learned the task. Okay, so how can we find these thetas? So say, for instance, we simplify the problem so to theta 1, theta 2. So in practice, there will be like 25 dimensions here, but in this case, for simplicity, I only have 2. So this is the space of all possible values for these parameters theta, these weights. Now we define a loss function. So a loss function is a function that, given a set of weights, produces a loss. So say, in this case, this can be the loss, and here we have theta 1 and theta 2. And basically for every value that of these model parameters that we have a loss. Right? So say that this is our initial point, then the corresponding loss is this much. Right? So typically we don't see this entire shape. Right? So we cannot easily say, well, this is the best one. So we need a way to go from this point to a next point which has a lower loss function. And so one way to do this is called gradient descent. We'll see later on. Basically what we do is we look at the gradient in this direction. This is the gradient of the loss in the direction of theta 1. And here, so this should be basically the gradient of the loss in the direction of theta 2. And we see that, well, we will update both parameters, but we'll see in this case, for instance, that changing theta 1 doesn't pay much, doesn't improve the model much, but changing theta 2 here does improve the model. And then we take a small step in this direction, and we do this for many times until we end up with a fit. Right? So what we have is a representation. We have a way to express our function f as a set of model parameters. We have a loss function for which we can evaluate a certain combination of model parameters, and we have an optimization technique which, given this loss, tells us how to adapt the model weights so that we can move towards a better model. Ultimately, we'll have found the best values for all these weights, and then the problem is solved. Yeah. And basically, all machine learning algorithms do some combination of these three things. Now, it's easy actually to build a model that's 100% accurate. We can just keep optimizing until we find a place where the loss is 0 or near 0. Unless we get stuck in a local minimum, that's also possible. Like there's a better solution here, which we don't find with this model. So we want to avoid that we find a solution that's very accurate on training data, but that does not work well on new data. Right? And this is typically called overfitting. So overfitting in general means that we build a model that is very good at predicting the training data, but bad at predicting the test data. In general, it means that we have a model that's either too complex or too optimized for the amount of data you have. Right? So say you want to recognize your mother in an image, but you only have 5 images, and you have to learn 1 million parameters, then yes, the model will find some solution that perfectly predicts those 5 examples, but may not work well on new data points, new examples. Right? So in that case, it's not a good model, and the way to solve that is to either collect more data, to collect a lot more images of your mother and other people, or by making the model simpler. So the different ways we can make the model simpler, this is called regularization. This will be a key thing in this course. We'll talk a lot about this. There are many ways to make a model simpler. For instance, if it's a neural net, maybe we can do with much fewer neurons. Or maybe we can change the range of values that we give to the weights. Right? So these are all techniques that make the model simpler. Or if you can, getting more data also helps against overfitting. Most parameters, most algorithms that we'll see have some high parameters, some user-defined settings that allow you to regularize the model. The opposite is underfitting. So here you have a model that's just too simple for the complexity of data. We've seen it before, right? So we've seen here, like in this case, this model is too simple to correctly model this data, while this one may be correct, maybe it's also too complex, right? But definitely this one is probably underfitting, right? So the model is too simple for this complex pattern that you want to learn. Now there are techniques that you can use to detect overfitting. A very powerful technique is bias variance analysis. Talk about it later. Sometimes you can also look at your learning curve to see whether basically your model is good at the train data but bad at the test data. We'll talk about that more later. And also later on we'll see something called ensembles. If one model is overfitted, we can build many models and then average their predictions, and that will reduce the overfitting. Oppositely, if we have a model that's too simple, we can build many simple models and then add up their predictions so that the sum of these models is more complex and then underfits less. Right? So ensembles are a very, very powerful way to solve this problem. We'll get back to that later. Here's just a visualization of under and overfitting. So here we have some points, blue points here. We want to learn a function to these points. The red line here is a true function, and the blue line is the one that we fitted. Right? So this blue line, that's the error. So the error here is about 1. So this is an 8-degree polynomial, which gives you a pretty good model with low error. Now I can try to use a simpler model. Right? So say I use a one-dimensional model. Well, this one-dimensional model does a reasonable job, but it can be better, right? We can try then to maybe increase. So every time I change this, it will compute the loss. So if I go to 2-degree polynomial, the loss drops. That's better. We can go to a 3-degree polynomial, and the loss is now very small. We can try 4, and it's worse again. Right? And you will see typically you will have this kind of U-shape as I try different models. And so the optimum model was here, this polynomial of degree 3. That was our best solution. Because the loss here was lowest. So this one here. If we make the model too simple, then it's underfitting. Right, the situation here. And if we make the model too complex, the loss goes up again, it's overfitting. So typically, most models have this sort of smooth behavior. So we have to tune our high parameters so that we find the sweet spot here. If we make the model too simple, it goes to underfitting, error goes up. If we make the model too complex, it will overfitting, and again the error goes up. So we need to find this optimal setting. This is generally called model selection. Okay. So the way to do that is, first of all, we need to split our data into training data and test data, and then we need an external evaluation function that we can use to vary the model, because the loss, the internal loss function used by this Bayesian linear model will always be minimized, right? So no matter which model I use, this will be the model that has the lowest loss function, the lowest loss value for that model. It doesn't mean that the model is good on test data, right? So we need two functions. We need an internal loss function to optimize to fit this curve, and we need an external evaluation function that we again choose. Well, typically the loss function, sometimes we can choose it a little bit, but often it's just tied to the algorithm because not every loss function works for every algorithm. The evaluation function we can freely choose depending on the application. Right? So whenever you have an application, you should carefully choose which evaluation function you want to use. Right? So if you work in the financial sector, typically the evaluation function is some sort of amount of dollars. If you work in health, maybe your evaluation function is the health of your patients. Right? So it has to fit the application that you want to solve. And so this evaluation function acts as a feedback signal. It tells us whether our model is doing the right thing or not, right? And how good it is. Right? Sometimes your best model is 60% accurate, and maybe that's not good enough, right? So your model is not useful. So it helps us to get some feedback and maybe make some decisions whether we should make the model simpler or more complex, or whether we should maybe use a different model altogether. So you need this to choose between models and also to choose between high parameters. Be careful that you not fall into this trap. Like you can, ad infinitum, try all different models, try all different high parameter settings until your model works. That kind of, you can always, if you tune this long enough, you will find a model that performs well. But again, this can be misleading because if you always test against a certain test set, then maybe that test set, what you do is you optimize on the test set, which gives you a model that works well on your test set, may not work well on future data. Right? So again, be careful, don't overdo this, and we'll also see some techniques that you can use, like cross-validation, which reduce this chance, but still be careful that you don't keep optimizing this ad infinitum, because if you do this too much, you will optimize on your test sets, and then your model will not work well. Yeah, so we need to split our data into training and test sets. So this is our test set. This is all our data, basically, plotted as in one dimension. We set part of this aside as a test set and part as a training set. So we can train our model in all this data, and then when we're done, we can test whether this model is okay. Now, if we need to make any other decisions, like if you have to tune the hyperparameters, or if we have to pre-process the data in certain ways, we cannot do this on test data, because if we tune the hyperparameters on test data, then obviously you will overfit on the test data. You should never do that. Similarly, if you clean your data, so if you are exploring, should I normalize my data, or should I clean my data another way? Should I select features and so on? Should I generate new features? Again, you should never use your test set to do that, because then your preprocessing will be specific to a test set that may not work well on new data. And we'll get back to it in one of the next lectures on evaluation. This is called data leakage. So whenever you tune your hyperparameters or your preprocessing methods on your test data, it's called data leakage. And this will give you misleading results. You will find a model that works well, but will work well in the lab, on your training data, in your data that you have, but it will not work well on future data. That's very dangerous. Yeah, so the way to avoid that is to split your training set into, again, training and validation set, and you can do whatever you want here. So you can build 1 million models on this training set and test them on the validation set, then use the best parameters, the best preprocessing, and then you retrain the whole thing on the entire training set, and that will then be the model to use in practice. You can test it to see how well it does. Okay. So what you do is on your training set, you optimize your on your training set, you optimize your model parameters theta, and you use loss function that will tell you which is the optimal set of model parameters. And then you evaluate that on your test data. So you can again do this many times, and then you can do this for different neural net sequences, right? So you build a simple neural net, you see, well, it doesn't work well, maybe you make it more complex in the outer loop. So we also typically notice by lambda. So we search for the optimal set of higher parameters. Every time we try new higher parameters, we have to refit our model parameters. And after we fitted that, we can evaluate that on the validation set, and until we find the best set of higher parameters, and then we have our final model. Okay. Now, having all these different training sets and test sets makes it sometimes tricky to know what to pay attention for. But the clear bottom line is that only your test set performance counts. Right? You should always evaluate the data. You should always evaluate your model on data that the model has never ever seen. Right? There is some way, so you can look at the performance of your test data to, first of all, to tune your model parameters to see whether you should make the model more complex or simpler, or to see whether your model converges. So this is very typical for neural networks, because you can give the data over and over again to the neural net to keep training, and you get some kind of loss function like this. This is the loss of your function given the model parameters. So it's good to see that your model is converging and it's not doing something like this. So it's not learning anything. So it's good to look at the training set performance in this case, but never view this as the optimal model, because it could be that your accuracy, for instance, doesn't do this but does this, right? And also the loss, the misclassification loss. And so it could be that your model gets more accurate over time, but then it starts overfitting, and then your loss goes down, but your external evaluation error goes up. Right? So you need to pay attention to that. So always keep a completely independent test set to evaluate your model. And if you have small data sets, we'll come back to this, but if you have small data sets, just the way that you split the data can have a bias. So if you have data, you split it randomly or however you do it. It could be that by accident, this test set only includes easy examples, right? And then your model looks good, but actually does not so good. Right? So a way to avoid this is cross-validation. You've probably seen this before. We'll cover it later, where we don't have a single train test, but we do this many times. Okay. Finally, we need to have a way to find the best data representation. Okay. So say we have the same data here. So in this case, we have to learn, well, not a complex model, but a model that consists of two variables, x and y in this case. But we can simplify this model if we can represent it better. If we can change the coordinates so that the data looks like this, then we see, oh, well, we don't need this input y. We can just make decisions based on this input x alone. Right? So this model is simpler than the one we would have to learn here. Right? So typically, if we can find a better data representation, the machine learning becomes a lot easier, and we can build good models. So whenever you want to transform the data to a better representation, this is called encoding or embedding. This encoding can be anything. It can be from numeric to numeric, or it can be from categorical to numeric. Like you can encode text, right? So then the input is just words, text, and the output is a numeric vector. Or it can be many things. Right? So anytime that we transform the data into a new representation, this is typically called an encoding or embedding. You can also do this end-to-end with deep learning. So what you do there is, I'll show an example in a minute. What you do there is you learn the representation as part of fitting your models. Look at that. So most machine techniques only work well if you give it a good representation of your data. Now, when your data is naturally structured, like having a table with meaningful columns, you can typically use your knowledge to engineer features. You can select your features, you can reduce them to fewer dimensions, you can scale the data. And if you do this well, then the model part becomes super simple, and the model will work well better, it will generalize better. So Andrew Ng, one of the best known machine learning teachers, often says that machine learning in practice is basically feature engineering. It's a lot about engineering how you represent the data to the model, and then the model, learning the model itself is not so hard. And if you have domain knowledge, nothing beats that. Even deep learning representation typically better than non-deep learning representations. But if you have domain knowledge in any way, and you can include it into your presentation, it typically makes learning much easier. So in the example of the iris data set, like knowing that leaf length and width is a good indicator for the type of flower, that's useful domain knowledge that you can use in representing your data. Now we've talked about deep learning before, right? So what's the main difference? And basically what it boils down to is that what deep learning does well is learning representations. If you look at the final layer in a neural net, this one here, what it does basically, it gets a sum of weighted inputs to make a decision. This is nothing more than a linear model. So the last layer is actually a very simple linear model. But what's interesting here is that the previous layers somehow transform this data X to a new representation after the last layer, which is easier to learn from. Right? And basically what these parameters here do is they learn how to transform this input image into a vector representation, which is easy to predict from. And this is basically what happens in deep learning models. Typically they have many layers, and every layer does some transformation of the input data. And after a number of these transformations, the data becomes so simple to learn from that a simple linear model can make accurate predictions. So for instance, in this case, we have a written number 4 here. Typically, you can look at the outputs. Well, every layer will have what's called multiple filters. We'll get back to that. But typically, this one image goes in the first layer, and then the number of filtered images come out. These are called the activations after each filter, which we'll explain in more detail later. What we'll see if we look at the activations is that after the first layer, a part of the model is looking at endpoints. It's looking at points, which are here. Other ones are looking at only diagonal lines. So some of these weights are learning endpoints. Some of these weights are learning where the horizontal lines are. Some have this kind of fuzzy nature and so on. And after the next layer, this is again simplified. Typically gets coarser because the number of neurons reduces. And well, the activations reduce because the filters get smaller. And we see that over time, yeah, you can still somehow recognize here diagonal lines here. But over time, these representations become less and less interpretable. But what it does is it represents this 32 by 32 image as 4 times 9 pixels. And these are then easier to make predictions from. So basically what happens in deep learning is that the input data goes through a number of transformations to give a new representation, a new embedding that you can then use to make predictions for. You can even replace this last layer by decision tree or an SVM, for instance. And sometimes this gives you better results than you can totally do that. Now, you may think that, well, maybe we just have to add many features to our data set, right? So if you have this problem here, why do you use 4 features? Why don't we just add, I don't know, 1 million features, and that will make sure that all the information is there and the model can learn from it? Well, it typically doesn't work because of the first dimensionality. And that's because of our inductive bias. When we build our models, we make assumptions. Assumptions such as if an image is similar to another image, it will have the same class. Right? It's kind of distance-based similarities and so on. But if you have many features, then computing distances in like 1,000 dimensions becomes quite abstract. And one way to visualize that is this little experiment, which is a few lines of code. You can look at the notebook. Basically, we draw an n-dimensional hypercube. Right, so this is a cube. So there's a cube. There's also there's a 2D cube. There's a 3D cube, a 4D cube, and so on. You cannot draw this, but a hypercube is a cube in n dimensions. If we now randomly sample points here and we compute how many of these are in the 1% boundary of this hypercube, we see that as the number of dimensions increases, all the points, basically almost all the points, will be close to the boundary. And that's because if you have to like randomly draw a point in one dimension, it could be anywhere. But if you have to do this over and over and over and over again, at least in one of these dimensions, the point will randomly end up at the edge. Right? And so this means that if you have very high dimensional data, all your points will be close to the edge, and basically all the distances between the points become the same. If you would draw the distribution of the distances between the points, right? So 2 points are like 1 apart, 2 apart, and so on. If you would draw the distribution, you will see that over time, as you add more dimensions, almost all the points have the same distance to each other. And if that's the case, then algorithms like KNN and SVM, they just won't work. And even neural networks won't work as well anymore. Right? So that's the curse dimensionality. Now, this has a lot of consequences. Because for every feature you add, you also need to then add exponentially more data to avoid disparsions, to avoid that there's no point similar to your new test point in your data. Right? And so any algorithm that uses distances, like KNN, SVMs, and so on, will be badly hurt by this. Right? Now, luckily, there's this blessing of non-uniformity, which means in many applications, the data is not randomly spread out in this space. It's typically in some kind of subspace. Yeah. So what you can do is select features or embed the data in lower dimensional representations so that we can still learn this. Right? So bottom line here is that you can add many features. That typically doesn't work, what does work typically is to reduce the number of features, preferably without destroying information, because that makes it much easier to learn from, because the algorithms work better. Now, people also often say that, well, you don't need a clever algorithm, you just need lots of data. In practice, you need both. Obviously, having more data is good, because having more data reduces the chance of overfitting. Also, having more data means your data is less sparse, and your model will still work well in high dimensions. But this is true, right? So there's no way around this. If you can get more data, then this is always better. But sometimes you don't have data, and you have to think about which algorithm to use. Now, why does more data help? Well, there's two types of models, basically. You have non-parametric models and parametric models. So non-parametric models, parametric models are the ones which have a fixed number of model parameters theta. It's a fixed number. No matter how much data you give it, it's a fixed number. If you have a neural network with 1 million weights, then you have 1 million weights. And if you have 5 examples, well, then you have to learn those millions weights with 5 examples. Right? Similar with linear models, you can build a linear model, you can give it maybe 20 coefficients in this case. And then you have to learn these 20 coefficients with 5 data points. So that typically won't work. So you have to reduce either the number of parameters, and you have to make the model simpler. But the more data you give it, the more complex the function can learn. So if you have a model, if you have 1 billion data points, then yes, you can easily learn a model with 1 million parameters. Right? And it will be very flexible, and it will learn whatever you want it to learn. Right? So these models are very good at benefiting from more data. Non-parametric models don't have a predefined set of weights, but the number of model parameters grows with the amount of data, like trees or k-inch nearest VM. You start with a simple model, and only when you give more data will the model get more complex over time. That's a non-parametric model. They can also learn any model that gives sufficient data. So if you have a lot of data, give it to your tree will become very complex. Of course, it will start overfitting. But in principle, these can also learn basically any model given data. And they're also typically good for small amounts of data, unless you don't have enough data to actually learn the thing that you want to learn. So if you have more data, then the bottleneck moves from data to compute, right? Because having to learn a model with 1 billion data points just means you have to compute a lot, right? And this takes time, takes memory, and so on. Finally, so all together, how do we build a machine learning system? Well, we have different components, and we'll cover all these components in the upcoming lectures. So first of all, we need to first of all need to pre-process the data, because raw data is rarely ideal. We need to scale the features. So say that your data is from -infinity to +infinity. That's simply hard to learn from when so you have one input x1, which goes from -infinity to +infinity, and you have another parameter x2, which goes from 0 to 1, then this parameter will have much more effect than that parameter. So to avoid that, we want to basically scale this so that all the features are in the same range. There's encoding, which means that if we have categorical features or text features, then we want to make these numeric. Because if there's numeric, then we can give them to a neural net or another algorithm that works with numeric data. Discretization is sort of the opposite. Here we have the numerical features. but we cannot fit the model well in the few numeric features that we have. So we can split this numeric feature in multiple features, and we can learn better from it then. We'll show some examples later on. Often also we have label imbalance. For instance, for credit cards, we may have a billion transactions from credit cards which are legal, and maybe only 1,000 which are illegal. This we call label imbalance. And we need to correct for that, otherwise our model will just ignore all the positive examples. We can do things like downsampling, upsampling, and smoothing, and so on, which we'll discuss later on. If you have any features, then we want to select the features. We want to remove the ones which are not interesting. We also sometimes can reduce dimensionality. We can do things like PCA to make the data easier to learn from. And we can also use pre-learned embeddings, like we explained before, like if we have this no netted many layers. So for instance, in comes an image or text, and out comes this embedding. Then we can use this embedding as input for any machine learning algorithm, any function f we want. Right. So in this case, we actually have multiple models in the system. We have one model that basically transforms the data, and another model that makes predictions. Then evaluation, because every algorithm has its own biases and there's no single best algorithm, we need model selection. We need to build trained test splits, we need to have evaluation function that makes sense, and we need to try different models to see which one works best. And finally, you have to predict based on independent test sets. And then finally, all these steps together, they create what we call a workflow or pipeline. So there's some process or user that gives us data. We ingest the data, we clean, transform it, we set aside some data for testing, we then build many models, we train many models, we test the model on test data, and we keep looping over this until we have the best possible model, and that model gets then deployed. Now, sometimes you should probably also include this transformation inside this loop, because that way you don't have any data leakage in your model. Finally, the final model isn't deployed, but then it's still not done, because over time your data can change. There's two things that can happen. So one is that the data changes naturally, like for instance, if you do climate modeling, the climate changes over time, which means that the model that you built on last year's data may not work well on this year's data. This is called concept drift. So the phenomenon that we are modeling changes over time. That means that we have to continuously retrain our model and adapt it basically to the new data so that it keeps performing well. And secondly, there's feedback. Sometimes by deploying the model, you change the behavior of the user, or you change the process that performed the actions. For instance, if you are Netflix and you have to recommend movies, then because you give recommendations, the viewing behavior of your users changes. This changes your data, which means that your model may not be accurate anymore and you have to update your model. Same thing with medical situations. If you have a good model that predicts treatments, your patients are treated better, their symptoms will change, and then your model again has to be updated because the people behave differently, or the input changed over time. That's all. Thank you, and we'll see you back for the second lesson.